In this video, we're going to show you how to study relationship between two or more numerical variables. Let's get started. In our first example, we have two numerical variables. One is called value, one is called size. Value is the value of the properties, a random sample of properties that we have taken in a city. Size is the size of the property, probably in square feet. In this example, value is called the dependent variable. It is the variable that we want to make inference on, or we want to make prediction in. Size, on the other hand, is called the independent variable. It's the variable that we have control over, or the variable that we can use to predict the value of y. So the question is, how do we study the relationship between the two variables? One way of doing it, of course, is to look at a graph, and the graph is called a scalar diagram. Excel has a facility to produce the scalar diagram very easily. The only thing is that we have to be careful about what we do when we generate the graph. The easiest way is to make sure that X, the independent variable, is the first column, and Y, the dependent variable, is the second column. So in this example, what we need to do is that we need to cut this column and paste it in column C so that X is the first column and Y is the second column. So that's exactly what we're going to do. And now, once we've done that, then we can produce the scalar diagram really easily. How do we do that? Well, we do go to Insert, and we go to this graph. This is Insert Scalar, and we click on it, and we will choose the one without anything, without the lines or without any segment that join the points. And what we have to do is to specify where they are. Now, we haven't done that, so let's just do that again. So the excuse me, the easiest way to do it is to highlight the X and Y variables, and then we do Insert, Scalar, and Scalar diagram. And you need to pay attention to what is the X variable. So in this case, you can see that X have value of 0 to about 3,000, which is exactly what the size variable is. On the other hand, the Y variable has a range from 0 to 800,000, which is exactly what we see in the Y variable. And if you want to take a better look, another way of doing it is to put your cursor on one of those points. You can see that this point, it corresponds to X value of 2523 and the Y value of 640. Right? So we can actually find it somewhere here. Right? So a scalar diagram is nothing but a graphical representation of all these pairs of values in the XY axis. And by doing that, we can begin to see whether there is a pattern. So for example, when we look at this, we can first of all look at the direction, whether when X increases, Y tend to increase, or the other way around, when X increases, Y tend to decrease. So in this particular example, when X increases, Y tend to increase. So we call this relationship a positive relationship. The other thing that we can look at it is that we can look at how strong the relationship is. And the way to look at that is how strong, how close are the points scattered around a line. Now, what we can do is that we can actually just right click on the points and we say add trend line. Now you can actually see that there's a trend line, and we can obviously format the trend line and make it look linear. We can actually put the equation on the chart of the trend line. You can also put something called the R square on the trend line, which we're going to look at, right? So by doing that, you can now see how close are these points scattered around this trend line. The more closely they are to the trend line, the stronger the relationship. That means the better we can in terms of predicting the relationship between X and Y. So in this particular case, the relationship is not bad. It's not that strong, but it's strong enough. So we look at direction, positive or negative, look at strength, whether they are strong, weak, or non-existent. And the third thing, of course, is to look at whether the relationship is indeed linear. Now, how do we know that the relationship is linear? Well, it's rather subjective, but if you draw a straight line forward, and you can feel that, oh, the straight line represents the point quite closely, then the relationship seems like to be a linear relationship. So in this particular case, I would say that the relationship is linear. So if you want to use one sentence to describe this relationship, we would say that there is a strong positive linear relationship between X, which is the size of the house, and Y, which is the value of the house. So graphically, we can see by just looking at the scalar diagram whether number one, X and Y has a relationship, number two, whether the relationship is linear, strong, positive, or negative, and so on. The next thing we want to do, of course, is we want to use one number to summarize this relationship. And the way to go about doing it is to use a number called the correlation coefficient. The correlation coefficient is one of the many numbers that statisticians has developed to measure the strength of linear relationship between the two. And there's a formula that you can use to calculate. In Excel, you can use a function called correlate. So C-O-R-R-E-L, that it would be the function that we can use to calculate the correlation coefficient between X and Y. And what we have to do then, after we spell out C-O-R-R-E-L, we have to spell out where the data is, right? So for X first is B2 to B62. That is the data that we have for X. And then obviously for Y would be C2 to C62. And notice that the first row is not included because this function does not accept the labels. And if you enter that, we have a number 0.9477. So the higher the number, obviously, is the stronger the linear relationship. But this number is designed in such a way that it's between -1 to 1. So in this case, the number is really close to 1. So we probably can say that there is a strong positive linear relationship between the two. Now, in the graph, as we did is, we actually can produce R squared. Right? R squared is 0.8982. R squared is nothing but the square of the correlation coefficient. Right? So if you take this number, H21, and then you square it by multiply by itself, H21, and you should have 0.8982, which is exactly what the numbers here. So, so the question is, why would we use this number also? Well, this number has a particular interpretation. This number means that that number represents the percentage of variability of Y that can be explained by the variation of X. So let me just write it down to you. So we say 89.8% of the variation of Y can be explained by the linear relationship with X. And I'm going to make it bigger so you can actually see. Right, so maybe we should also make all this number bigger so you can actually see what we say. Right? So this number, this is the correlation coefficient. Right? So this is a measure of how strong the relationship is. It's actually a number that we use all the time. Right? And this number, 0.898, which is the square of this number, has a name. The name is called coefficient of determination. And statisticians tend to use that number as well because, why? Because it has a particular, let me just make sure that we make it big, right? So this is the coefficient of determination, and its interpretation is such that these represent the percentage of the variability of y that can be explained by its linear relationship. So when we have two independent two numerical variables, and we want to study the relationship, we can use the scalar diagram to represent the relationship graphically. We can use R, correlation coefficient, to represent the relationship numerically. And we can also look at R squared, which represents the percentage of the variability that can be explained by the linear relationship. Now that we see that there is a linear relationship between the two by looking at the graph, one thing that we want to do, of course, is that we want to ensure from a statistical perspective, this result is significant. We were going to go to produce a set of tables that Excel could produce. You can use Excel to produce that for that purpose. And once the relationship is confirmed from a statistical perspective, then you can use the relationship, the equation, for prediction purposes. So for example, when we draw the scalar diagram, we're able to draw this line, and the equation of this line is also printed. Well, once the relationship is confirmed from a statistical perspective, then we can use this equation for estimation and prediction purposes. So how do we go about doing that? Well, we use a program under data analysis. So how do we go about doing it? When we go to data on the data ribbon, and then we go to data analysis. This is the data analysis add-in that we have used. And we go down and we find regression. So regression is one of the program under the data analysis add-in, and we say, okay. And when we do that, what you have to do is you have to specify, and you have to tell the system where the Y range is, where the X range is, and so on, right? So Y, in our case, is this column. So we just have to specify the column of the values of Y. And likewise, we have to specify the column for the value of X. And notice that in both cases, the first row, we have labels, so label in the first row, so we check that. And then the rest doesn't really matter because it doesn't, Excel actually has some issue with the program. So whether you specify or not, the Excel is going to produce the confidence interval anyway. So if you say, okay, that's all you have to specify, the X value, the Y value, whether you have labels in the first row, and where do you put the output. So we're going to put the output in a new worksheet, and that's it, right? So now there's 3 sections in the output. So let's go through the sections quite carefully. The first section is what we call regression statistics. It gives you some ideas about the relationship from a descriptive perspective. So for example, we have something called R squared. R squared is the coefficient of determination that we talk about. And so R squared can also be calculated here. Now, multiple R is not exactly correlation coefficient. When the relationship is positive, multiple R is the same as the correlation coefficient, right? With 0.9477 is exactly what we calculated, 0.948. However, if the relationship is negative, these numbers still maintain positive. So this is not exactly the place where you want to pick up correlation coefficient. You have to use the correlate function to calculate that. Adjusted R squared is not meaningful if you only have one independent variable, so we're going to ignore it for now. Observation is the number of the sample in the data set. So in this case, this is the sample size, which is 61. So the next section of the output is the ANOVA table. Right? The ANOVA table have a very similar structure comparing to the ANOVA table that we learned when we learn how to compare several population means at the same time. So let's go through them very quickly. So there are two sources of variation. One is called regression. So this is the variability of y due to regression. And then there's also variability due to residual. Now, some textbooks will also call this error. So this is just a matter of terminology. So some software and textbook will call it error. In this case, Excel will call it residual. And then you have total. So basically the same thing as before. You break the total variability of y into two components. One is the variability due to regression. The other one is variability due to error. And the degree of freedom is calculated as follows. So the best way to do it actually is to figure out the total degree of freedom first. The total degree of freedom is always sample size minus 1, n minus 1. So n is equal to 61, so n minus 1 is equal to 60. The next number that you should figure out is regression. The degree of freedom regression is the number of independent variable. So in our case, we have one independent variable x. So degree of freedom for regression is 1. And because of the fact that you have to add up these two degree of freedom to get to the overall, so you can figure out 59. 59 is actually 60 minus 1. Now, you can also use a formula. The formula is n minus p minus 1. P is equal to 1. So n is equal to 61. So n minus p minus 1 is equal to 61 minus 1 minus 1 is also equal to 59. But the best way, of course, is to figure out 1, figure out 60, and this one is just 60 minus 1. The sum of square is the variability due to regression and variability due to error. The calculations are extremely complicated. I would never suggest anyone to try to do that manually, and system will be able to produce that. And what you need to do is to understand the fact that these two sum of squares equal to the sum of square total, just like other ANOVA table. The next column is MS. MS stands for mean square. So mean square is basically the sum of square divided by the degree of freedom. So the first one is MSR, so mean square for regression. So how do we calculate mean square for regression? You take SSR, sum of square for regression, divided by the degree of freedom, which is same. The next one is MSE. MSE is mean square for error. So mean square error is equal to the sum of square error divided by the degree of freedom. So you take 46408.79 divided by 59, which is equal to this. So mean square for regression, mean square error. And then you take these two numbers, the ratio of these two numbers is the F statistics. So the F statistics 520.3776 is actually equal to 409,323.6 divided by 786.5898, right? So you take this two mean square, form the ratio is the F statistic. In Excel also give you the p-value, except Excel wouldn't call it a p-value, except it calls significant F. Significant F is the p-value that corresponds to the F statistics. Now, you look at this number is 5.88785 E minus 31. Whenever you see an E in the number, that means that this is a scientific notation. So you want to convert it into the ordinary notation. This is a very small number, by the way. So how do you do that? You can just go to this number and you go to format, and you say format cell, and if you say number, you can see that if I have all these decimal places, only after 31 decimal places, there's a 1. So this number is almost 0. It's very close to 0, right? You can see that there's all these 0, all these 1s. Normally, we would just keep this number for, say, 4 decimal places, right? And And if you keep this number to 4 decimal places, that number is pretty much 0. So this, at the F statistics, as well as the significant F, which is the p-value, can be used for testing purposes. So let's just try to do that. Now, what are we trying to test? Well, this part, we're using it to test whether the regression model is significant. So the null hypothesis is that the regression model is significant. Statistically significant means that this is not due to chance. It's not significant, sorry. And so if this is the null hypothesis, the alternative hypothesis, of course, is equal to the regression model is significant. Okay, so I'm going to just copy it down here. And so let's go through the 5-step, right? So the second step, of course, is set alpha. Alpha, let's do 0.05. And so if you're using the p-value approach, we say reject x0 if the p-value is less than alpha. And where's the p-value? The p-value is the significant F, right? So the p-value, and you can, if you're using Excel, you can pick up this number right away. It's 0.000. Of course, this is less than 0.05. So we reject x0, right? So we say the regression model is significant. So this is how you do a test to see whether the overall model is significant using the p-value. Now, if you do that for critical value, we can do the same thing. Now, when we do the critical value, obviously the rejection rule is we have to find the critical value. So how do we find the critical value? Well, this is an F test. So you have to go and find the critical value for an F test with degree of freedom 1 and 59, right? So 1 and 59. So let's just see 1 and 59, the graph will be like this. And you have to find the rejection rule on this, right? Now, if this alpha is 0.05, that means the lower tail is 0.05. This tail is 0.05. So if this is 0.05, then this is 0.95. So it's actually, when you do critical value test, it's very important for you to draw the picture, right? So if this is 0.05, this is 0.95, right? So what we need to do is to find the critical value, right? So let's see the critical value. The critical value is, it can be defined as equal sign F dot INV, right? So this is how you find the point that corresponds to alpha. And it's 0.95, as I showed you in the graph, right? Sorry, I cannot do that. Let me just do it here, 0.95. And then the numerator degree of freedom is 1. The denominator degree of freedom is 59. And that's how you find the critical value, right? So the critical value, if you only look at 3 decimal places, and is 4.004, right? So you say reject x0 if the F statistic is bigger than 4.004, right? Now, obviously, you can use the table if you want to use the table. So the table would be like this. You go 1, the numerator degree of freedom is 1, and then the denominator degree of freedom is 59. Unfortunately, most tables will not have 59. You have 60 or 40. Theoretically, you should always use the degree of freedom that's next lower, right? So you should use actually 4.8, right? But if you use 4, I don't think it would make a difference in this case because the result is something significant. Okay, so but if you use Excel, that would be the way to find the critical value. And obviously, you say since F is calculated by Excel to be 520.0 0.3776. So this number is much bigger than 4.004. It doesn't matter what value that you use, right? So you will reject. So this is how you perform a statistical test to see whether the overall model is significant. Another way of doing it, of course, is that you can also see whether the variable x is significant. The relationship between the variable x and y is significant. And the way to go about doing it is to use the third part of the tables that is generated, and you go to size, right? And you go across, you find the t stat, right? So t statistics and the p value, right? So that's the number that you can use to perform a test to see whether the variables are significant. So another way of testing the same thing, the reason why it's the same thing because the model has only one variable. So the overall model significant means this variable is significant. This variable significant means the overall model is significant. So by the t-test is another way of doing the same thing. But the way to do it is to use t-stat and the p-value here. Okay, so how do we do that? Well, let me just write this down for you. We say x0 means that the variable size is significant. And x0, of course, is not significant. And the alternate hypothesis, the research hypothesis, of course, is that the variable size is significant. Okay, and so let's alpha equal to, say, 0.05. And then if you use the p-value approach, so we say reject x0 if the p-value is less than alpha. And if you use Excel, the p-value is calculated right here. Now, again, can you see 5.98 E minus 31? So this is not 5.98. This is actually a very small number. Okay, so let's just do the format and do 3 decimal places, and that number would be 0. Right? So we say since the p-value is 0.000, of course it's less than 0.05, so we reject x0, right? So in reality, what you can do is just look at this p-value and this p-value, and you know that the result is significant. Now, if we were to use the critical value approach, then you would do the following, right? So the null and alternate hypothesis is the same thing, the alpha is the same thing, the critical value is different. Now, when you calculate the critical value for t, you need to know about the degree of freedom for the t-stat. So what is the degree of freedom for the t-test statistics for this variable? Well, it's actually very easy. It's actually 59, right? If you want to know about the formula is n minus p minus 1. But in this case, it's just the degree of freedom for error. It's always a degree of freedom for error, right? So the critical value, so if you want to use Excel to do everything, the critical value, of course, is equal to t dot inv. And in this case, you have to be careful. The F test is always a upper tail test, as we talk about in ANOVA. The T test is a two-sided test because we don't really care about whether the relationship between y and x is positive or negative as long as it's significant. So if you're performing a t-test for the coefficient here, this is always a two-sided test. If it's two-sided test, it would be 0.025. And the degree of freedom, as I said, was just 59, okay? And the number is negative 2.001. Now, in fact, it's very interesting. If you take this number and you square it, you get this number, okay? That's how the mathematics work. So we say reject x0 if the t statistic is less than negative 2.001. 2.001 or t is bigger than 2.001. So remember, if you use a t-test to see whether the relationship is positive, is significant, then it's always a two-tailed test, right? So now we can make the conclusion. The t-test is calculated for you, right? The t-test is 22.81, so 22.81. Of course, this number is bigger than 2.001, so we reject x0. So in this example, we just show you how to use the output from Excel to perform statistical significant tests to see either the model is significant or equivalently whether the independent variable is significant. So that concludes the example for the simple regression. In reality, we actually would have several independent variables, 2 or more independent variables. So we're going to look, the next example we're going to look at is what we call multiple regression, when we have more than one independent variable. So in multiple regression, you have one dependent variable, in this case, the value of the house. But instead of just looking at the size of the house, we also look at the number of bedrooms. Like the number of bedrooms is 2, 3, 4, and so on. Okay. So in this case, you have 2 independent variables, size and number of bedrooms, and you have one dependent variable. And you want to see whether the dependent variable y has a linear relationship with size and number of bedrooms. Now, to do that, you cannot really look at a graph anymore, because now you are looking at 3 dimensions, and it's really difficult to depict a relationship in 3 dimensions. So instead, we're going to just rely on the numbers and the text. So how do we generate the numbers was to do the analysis? We use the same program, right? So we go to data, we go to data analysis, and we go to regression, and we will specify what the y range is, right? So the y range is this, right? Now the x range, because of the fact that we have 2 variables, you have to specify both. So therefore, when you do regression analysis in Excel, all your x variables should be together. They should be contiguous. You cannot have 2 x variables here and then an x variable on the other side of y. If you have that situation, it won't work because you cannot really specify it properly. So before you do anything, you should make sure that all the x variables are lined up in the same side and they are contiguous. So in this case, they are. So we can actually just specify the x. So x has, we have 2 variables. So we just have 2 columns. So we have 3 variables, you highlight 3 columns and so on. Okay. And this is labels. And then we put it into the new worksheet, and so that's that, okay? So the output would look exactly the same as before, because they are, and the work would be exactly the same as before. So let's go through them very quickly. All right, so the first number, multiple r, is not meaningful anymore. R squared is is a measure of the strength of the relationship, and what is the interpretation again? Let's just write down the interpretation again. So R squared is 89.889. So we say 89.9% of the variability of y can be explained by its linear relationship with x, but x has 2 variables, right? So we have size and number of bedrooms. So you need to mention both. Okay, so I'm going to make this everything bigger so that you can actually see. All right, so this is the interpretation for R squared. Now, on the other hand, we have something called adjusted R squared. Adjusted R squared is R squared adjusted for the number of independent variables, because when you do linear regression, the more independent variable that you put into a model, the higher the R square. So R square sometimes is higher, not because of the relationship is stronger, it's just because of the fact that you have more independent variable in the model. So in order for us to compare between different models that has different independent variable, we take the R square, we adjust it for the number of independent variable. And so therefore, when you have more than one independent variable, adjusted R square is the number that you should use for comparison if you want to compare models using the R square as a benchmark. So the interpretation of adjusted R square is exactly the same, except what? Except that we have to say something at the end, right? Adjusted for the number of independent variable, right? So because of the fact that there's two independent variable, R square would be adjusted by that. And so the number is a little bit smaller in this case. So it's still 89.5. Right, so 89.5 obviously is a very good number. The rule of thumb is that anything that is 0.9 is 0.85 is very, very good. Now, what do you mean by good? Well, it depends on the subject matter, right? So in business, R square tend to be higher than other disciplines, like for example, sociology or psychology. So 0.85, 0.89 is good. They're good number. They're indicator that there's a relationship, a linear relationship between the dependent variable and the set of independent variable. On the other hand, if the number is 0.2, 0.1, 0.3, then you probably are looking at a relationship that is not going to be very helpful. So that's how we take a look at the numbers and see the relationship from a descriptive standpoint. But if you want to use the relationship, you still want to go through the statistical testing to see whether the model is statistically significant, right? So again, for the middle sets of the table, the ANOVA, this table that we can use to test whether the overall model is significant, right? So let's just copy down what we did, right? So we're going to just basically do the same thing, right? And we do exactly the same thing here, right? So the null hypothesis is the model is not significant. The alternate hypothesis is the model is significant. We set alpha is equal to 0.05. And if you use the p-value approach, we say reject x0 is the p-value is less than 0.05. And then, of course, the p-value, right? So this p-value, significant f, is the p-value for the f statistics. As you can see, that number is 0. So we can say that this, obviously the overall model is significant. Now, again, if you want to do the test using the critical value approach, we can do the same. So instead of retyping, we can actually just copy the thing here, except that we need to make some adjustment. Why? Because if you look at the F statistics, the degree of freedom for regression is 2. Why 2? Because we have 2 independent variables. The overall degree of freedom is still 60 because the sample size is 61. So the overall degree of freedom is n minus 1, which is 60. And therefore, the degree of freedom for residual or degree of freedom for error is 60 minus 2, which is equal to 58. Okay? So when we look at the F test has the 2 degree of freedom, which is 2 and 58, not 1 and 59, right? So 2 and 58, and that's how you find the critical value, and the critical value is 3.156, right? So we say reject x0 if f is bigger than 3.156. And again, what is f? F is equal to 259. 258, right? So if you look at this number, well, that number is actually has a lot of decimal places. So the F is equal to 257.97. Obviously, that number is still much bigger than much bigger than the critical value. The critical value is 3.156, right? So again, if you use the critical value approach, we would reject the null hypothesis as well. Now, so the remaining work is for us to look at the individual variable. So unlike the simple regression scenario where we only have one independent variable, we have two independent variables. One is called size and one is called number of bedrooms. We have to, if the overall model is significant, we actually have three scenarios, right? We have a scenario when both independent variables are significant, or size is significant, but number of bedrooms is not significant. Or we can have the number of bedrooms not significant, but size is not significant. Okay, so again, if you want to use the p-value approach, you can actually look at the p-values, and you can see, right, which one is significant, which one is not. So you can actually see that based on the p-value, size is significant, but the number of bedrooms is not significant. Okay, so in this case, the overall model is significant, and the reason why the overall model is significant is the fact that size is significant, but the number of bedroom is not significant. So what we do in practice is that if this is what we found, we're going to rerun the model, and we're going to drop off number of bedroom, and we only keep size as the only independent variable, and we run the model and use it as a final model for prediction or for estimation. Now, let's just do the test and see what happened. If you were to do the test, I'm going to just do the critical value approach because the p-value approach is easy. We have done it, right? All you have to do is look at the p-value here, and you can do that. If you do the critical value approach, let's see, right? So, so let's do the size first, and then we can do the number of bedrooms, right? So, so the null hypothesis is that the variable size is not significant. The alternate hypothesis is the number of the variable size is significant, right? Alpha 0.05. What's the critical value? Well, the critical value is a t statistic with how many degree of freedom? The degree of freedom is always n minus p minus 1. In this case, p is actually equal to 2. So n is 61. 61 minus 2 minus 1, which is equal to 58, right? Or you can just pick up the 58 here, right? So the critical value is actually equal to t dot inv 0.025. Remember, when we do the test for each of the coefficient, they are always two-sided for the t distribution, and the degree of freedom is 58 instead of 59. So the number is negative 2.002. So we will say reject x0 if t is either less than 2.002 or bigger than 2.002. And what is t? What's the t value correspond to the size? The t value correspond to the size is 15.87, right? So the good thing about using Excel is that Excel actually do all the calculation for you. You don't have to do anything. So this is 15.87, right? And obviously that number is bigger than 2.002, and so on. Now you say if I were given these two numbers, how can I calculate the test statistic? Well, the test statistic is actually equal to the coefficient divided by the standard error, right? So for example, if you calculate the test statistic for size, you can actually see that this is equal to 0.197786 divided by 0.01246. Right? That's actually how to calculate the test statistics for size, right? So if you don't believe me, let me just copy it and calculate it and see whether you get the answer, right? Okay, so right, so you say, oh, how come this is slightly different? Well, because of the rounding, right? So I didn't do all decimal places, and 0.124 I also have a typo 59826. I think now this time will be much closer, right? So you can actually see that there's obviously rounding error, but it's close enough. Okay, so if you take the coefficient divided by a standard error, you would get the test statistics. Okay, so if you were to perform the same test for the number of bedrooms, the critical value is actually exactly the same. Why the critical value is exactly the same? Because the critical value will be found for this degree of freedom. So the only thing that is different for the variable number of bedroom is the hypothesis different. So the variable number of bedroom is not significant, right? And the alternative hypothesis is that the variable number of bedroom is significant, and the decision is exactly the same. Why? Because the degree of freedom is exactly the same, but then the test statistics is different, right? The test statistic for number of bedroom is 0.668, right? So 0.668, 0.668. Is this number 0.668 bigger than 2.002? It's not, right? So it's not greater than 0.008. So therefore, we do not reject the null hypothesis. Do not reject, right? So the logic exactly the same. The difference here is, right, is this, right? So because the test statistics is much smaller and it's not bigger than 2.002, so therefore you do not reject. Okay, so this is how you assess the statistical significance in a regression model. And this is the basics in terms of how we get to it. Now, once we confirm that the model is good, so suppose we, in this case, we shouldn't do it, but suppose the number of bedrooms is also significant, we can actually write out the equation, right? So the equation is estimated value of a house is equal to, right? So this is the intercept. Now the intercept is there for mathematical convenience. We never do anything from a statistical standpoint. We just let it be. We do not do any statistical tests and so on, right? So this is 175.06. Let's just use 2 decimal places plus 0.197.198 times size plus 4.327 times the number of bedrooms. Right, so this is how you write down the equation. If all of them are significant, this is how you write down the equation. And once you write down the equation, you can actually use it, right? So for example, if I want to estimate a house, estimate value when size is equal to 1,500 and number of bedroom is equal to 3. How can we do that? Well, we just have to put in size equal to 1,500, 3 into the number of bedroom, and we can calculate, right? So we can actually just take this equation, if this equation is what we want, and we can just put it there, and then we can replace size with 3, 1,500, and then number of bedroom with 3, and the value would be 485,000. Okay, so if you look at that, it just basically you put 1,500. You put 1,500 in for size, and you put 3 in terms of the number of bedrooms. Okay, so that's how you use the equation. So that's the basics that we need to know about regression analysis. There's actually a lot more that we can talk about. For example, residual analysis for checking assumptions and so on. But this is beyond the scope for this video. So for the purpose of this video, this is it, and I hope that you enjoy it, and I hope to see you soon. Bye for now.